Continue on here, maybe. Hopefully with the light show that we got going. All right. So we've been talking about kinetics here in this chapter, and last time we talked mainly about how to calculate the rate law from experimental information. Remember that the rate law looks something like this. And again, as we talked about, the rate law is based only on reactants when we do it. Again, we typically will have some type of table where they will give us the concentrations of the reactants. They'll also give us the initial rate typically. And usually you'll have multiple sort of experiments that are being performed. And what we want to do, as we talked about, is sort of use sort of the equation that we talked about, which is sort of the rate 2 over rate 1 is equal to k times a to the x and b to the y, and k a to the x and b to the y. So once again, what we're looking for when we analyze this table is we do want to choose, a couple of entries where one of the concentrations basically remain constant and the other one varies. Bless you. And what that will do is essentially give us only really one unknown, and it will allow us to really figure out each of the orders by doing so. So for example, you'll end up with something like 4 when these guys cancel out. Maybe these guys completely cancel. 2 to the x, and then x equals 2 in that particular case. So remember as well, if you don't have really nice numbers, you can't sort of see it. You can't take again the natural log of both sides there and divide out both sides. So again, you could take like the natural log 4 is equal to natural log of 2x and divide the natural log 2, for example, to both sides there. Get your x value that's equal to 2. Once we get the actual orders of the reaction, once we get the x and the y, as we talked about, that will give you the overall order. If it's just those two, if you have 3, you would add one more to the mix there. And once we have the completed rate law with the orders, we can then go back and solve for the value of the rate constant. Remember, when you're solving for the value of the rate constant, you can choose any entry from the table. They all should give you really the same number since they are all constant. It's a rate constant. So for that particular reaction, since they're all run under the same conditions, they really all should give you the same K value when you calculate it. Again, you just can't mix and match, obviously. So either use all of entry 1, 2, 3, 4, whichever one it may be. We, towards the end there, got into more specific classification of reaction, which was a first order reaction. And in a first order reaction, you basically can have either one reactant where its order is 1, or again, another one is perhaps you may even have 2 reactants where the one's first order and the other one is 0 order, which would also still give you a overall first order rate for this particular reaction. When we have a first order reaction, there's a few things that are really important to remember, as we talked about. First off, the value of the units of the rate constant are typically reciprocal seconds. As we talked about, they don't necessarily always have to be seconds, but they are really some unit of 1 over time, basically. So again, they can be minutes, 1 over minutes, 1 over hours, days, weeks, whatever it may be. But very commonly, in probably this chapter, we will mainly see it probably as reciprocal seconds, but again, it can be definitely something else. With that, we have an integrated rate law, which is the natural log of A is equal to the natural log of A naught minus KT. This is really like your final concentration of A. That's like your initial concentration of A. That is your rate constant. And as we talked about last time, that there is time. Again, not temperature, which sometimes people automatically see T and think temperature. The other important thing on this one, again, as we mentioned, is the units of these two here at the end. They both have some element of time in terms of their units. So they do need to be the same unit. Otherwise, again, they're not going to cancel correctly, and you will be off when you do your calculation. There's also a half-life equation specific for first order, which is the natural log of 2 over K. Natural log 2 is 0.693 divided by the rate constant there. And again, sometimes you may have to use sort of both of these sort of equations together. And that's usually a case where maybe they give you the half-life, but not the rate constant. So a lot of times you'll use the half-life equation to figure out the rate constant, and then you can kind of use the integrated rate law to figure out whatever you may be looking for. If we rearrange the integrated rate law here, we get something like the natural log of A is equal to minus KT plus the natural log of A naught. And this is in the form of a straight line, which in kinetics is pretty much what the linear relationship everybody wants. That is our y, again, is equal to mx plus b, which is the equation for a straight line. This gives us the typical first order graph that we will see, which is the natural log of A. And then on x would be time. And this will give us a usually negative sloping line here, where the slope of that line equals minus k. And as we talked about before, that is a negative slope line. That is a negative in front of the k, which means that your k value will end up being a positive number when you take it from the graph there. So those are really sort of four important things for first order. The units, again, because they won't always tell you exactly what order reaction you're using. The integrated rate law, which allows you really to figure out time sort of concentration changes. So as concentration changes, how time moves, and the half-life there, and our graph, what it looks like. First order kinetics is, again, how radioactive decay happens. So all radioactive decay, anything that's a radioactive element that goes through decay, which as it decays every so much time, does follow first order in terms of their kinetics. Any questions on any of that stuff there from last time? Yeah. So here is a sort of first order reaction. Again, we get a very nice linear line here when we have the natural log versus time for this particular reaction here. And once again, our slope would equal our minus k, which would be the change in y over the change in x to calculate. So why don't you try one here? The reaction is 2A goes to B is first order, has a rate constant of 2.8 times 10 to the minus 2 reciprocal seconds. How long will it take to decrease from 0.88 to 0.1? Okay, let's take a look. So first off, they were nice enough to tell us that it is first order, but that's not always the case. Once again, we do have the rate constant given to us, and we do see the units associated with the rate constant. So that automatically should tell you that's first order. And again, we should obviously use our first order sort of equation that should go with that, our formula. So by seeing those units there associated with the rate constant, I know it's first order. So we definitely want to use our equation here. And at this point, we do have our initial concentration, which is 0.88. We have our final concentration, which is 0.14. And that's pretty much all we need here to put in. So we'll go with natural log of 0.14 equals the natural log of 0.88 minus k, which is 2.8 times 10 to the minus 2 reciprocal seconds, and our time. So we're going to clean this up. We basically are going to take the natural log of this side and then subtract that, right, to the other side. And then divide by this. So just subtract it. So if I do that here, I'm going to take the natural log of 0.14, and then we'll subtract it from the natural log of 0.88. That's going to give me something like, looks like minus 1.838279 equals minus 2.8 times 10 to the minus 2 reciprocal seconds, and t. So we're going to then divide this obviously to the other side. And when we do that there, we will get time is equal to about 66 seconds in this case. Remember that we also need to take the negative to the other side, right? So that's how we get to our positive number on the left there. Any questions on that? So in this reaction, it'll take, again, about a minute for the concentration to drop down from 0.88 to 0.14. Any questions on the calculation? All right, so we talked about half-life there, and again, specifically for first order, the half-life is the natural log of 2 over the rate constant. Again, in this particular case, the half-life for a first order reaction is not dependent on any type of initial concentrations or anything like that. It's really just dependent on sort of the rate constant. Also, if you by some chance can't remember the half-life equation and you're not too bad at math, I suppose, you could also derive the half-life equation by substituting this in for that and solving for t, and that will get you your half-life. Yes. What's that? I probably wouldn't maybe do it all at once. If I was to punch it into a calculator, I would start by doing the natural log of 0.14. Yeah. Maybe hit equals. And then I would subtract it from the natural log of 0.88, hit equals. And at that point, just divide it, take the whole number you got in your calculator, divide it by the minus 2.8 with your exponent button, -2, something like that. Yeah. It is, you do want to take the natural log of both of those numbers and then sort of subtract them. And that's different than if you did a math move where you took the natural log of the sort of the guys divided by each other. So it's a little bit different than that. But that's probably the easiest way, just kind of get a number and subtract it. Other questions? Yeah. Yeah, so typically when you take kind of the natural log of a number, you kind of lose the units, to be truthfully honest with you. But they do also cancel out because mathematically, that's the same as basically one concentration over the other. So that's how they sort of really also cancel out. Other questions? Yeah. So basically, when if you have like the natural log of like a concentration over concentration, it's the same as if you kind of spread them out as separate ones as well. And then that's where your molarities technically would sort of cancel each other out when you do that part of it. Other questions? Okay. All right, so when we do this, what is the half-life if it decomposes with a rate constant of 5.7 times 10 to the minus 4? And how do we know it's first order? Yeah. All right, so see what you get for the half-life of that one now. Okay, so looking at this, once again, we'll kind of answer the second question first there. We see those units of reciprocal seconds off of the rate constant. So that's definitely how we know it is first order. That will direct us to the appropriate first order half-life equation. As we will shortly see, there are some other equations for the half-life for different orders of reactions. So we do want to use it specifically for first order. That will get us our 0.693 basically divided by our 5.7 times 10 to the minus 4 reciprocal seconds. And in this case here, looks like we're gonna get something like 1216 seconds as the units. Obviously it comes to the top when we divide it. Sig fig wise, got a couple of numbers there, so maybe like 1200 seconds or something like that would work. Any questions on that there? Okay, so really important, as I mentioned before, you do need to obviously know this, and you do need to know this, and more importantly, sometimes is knowing we're dealing with a first order reaction when we do see those units. So half-life, as we talked about, really is the time it takes for half of whatever you started with basically to disappear. And again, as we can see here, we got half the circles, half left, half left. You know, after about 10 half-lives or so, should be pretty much gone at that point, whatever you're dealing with. And it should be about the same amount of time for every half-life as it sort of decomposes. All right, so let's take a look at this one here. The reaction is first order with the rate constant of 2.9 times 10 to minus 4. What is the concentration of SO2 Cl2 at 865 seconds if we started with 0.0225? Let's see what you come up with here. Okay, let's take a look. So once again, they did tell us what order it is, but they may not always. But again, we can see our units on our rate constant, which tells us that it is first order. So in this particular case, we'll use our first order equation. Natural log of A is equal to natural log A naught minus KT. And in this particular case, we are looking for really our final sort of concentration here. So we do have our initial concentration basically of 0.0225. We're kind of looking for that final. We have our rate constant given to us at 2.9 times 10 to the minus 4 reciprocal seconds. And we also have the time here, which is 865 seconds. So putting this in, we got everything on the right-hand side here, natural log of 0.0225 minus our 2.9 times 10 to the minus 4 reciprocal seconds and 865 seconds. So once again here, we do want to check and we're good. We do have the same units here of time on both of those. So we're not going to run into any issues. And again, that's not always the case. So you do want to watch out for that. We could clean up everything on the right-hand side here. We're basically going to take natural log, if my calculator works here, natural log of 0.0225, going to hit equals, going to minus, open a parentheses, 2.9 exponent -4 times 865. And if we do all that good stuff there, that's going to give us the natural log of A. It's going to be minus 4.04508997. To get rid of the natural log on the left-hand side, we basically got to take the E of both sides, right? And when you do that, those guys basically cancel, and that gives you A is equal to, and on most people's calculator, you can find that E above the natural log button is what you're looking for. And a little, and that will give us something like 0.0175, and the units here would be molarity to match the original units there as well. Any questions on that there? So again, that E is usually where you have your natural log. It'll kind of look something maybe like this or something like that. Let's see here. It does sort of make sense, right? This is sort of the final concentration, which means it should be less than the original. And it is less than half as well, which also makes sense because if you actually calculate the half-life, it's like 2,200 seconds or something like that, or 2,000 seconds. So obviously it's much less than half of it. All right. I'm gonna try another one here. Molecular iodine, first order rate constant. What is the half-life? I'm gonna use the first order half-life equation, which is different from some other ones. Here we are given the rate constant, so we could just plug in. And that will give us 0.271 reciprocal seconds. That's going to give us our natural log of 2 divided by 0.271. And I think it's 2.56 seconds, I believe. Yeah. Reading my calculator, right? That's fast or slow half-life. That's super fast, right? Every couple of seconds or so, it's pretty much half of whatever you have is gone, right? So it's going to go very, very quickly. Any questions on first order here? All right, so there are some other common orders of reactions that we do come across. So let's talk about the couple other ones that are important. The next type of reaction is going to be actually a second order reaction and is a little bit different in terms of sort of the formulas that we use for it if it is second order. You obviously could get a second order reaction by having like we see there, the order of the one reactant as second order. You obviously can also get a second order reaction if you had two reactants where they're each first order, would also give you obviously a second order reaction. So there are a couple different ways that you could kind of achieve that. Now, in terms of the rate constant, if we were to take this and rearrange and solve for the units, the rate constant for a second order reaction typically will give us our 1/molar seconds. And that again is what we saw in some of those earlier examples where we were just sort of calculating some of these things. That is typical what we see for a second order reaction. Much like a first order reaction is typically 1/seconds for the rate constant. 1/molar seconds is very common for our second order. Just like the first order, though, although it is seconds, it doesn't necessarily always have to be seconds as a unit of time. So it really is like 1/molar, some type of unit of time will also tell you that it is second order. So again, it could be like 1/molar minutes or molar hours. But again, most commonly 1/molar seconds is probably what you would see. It also has sort of an integrated rate law that does concentration and time dependence, and it is this one right here. It is 1 over the concentration of A, which is kind of like, again, our final concentration, and 1 over our initial concentration, and the rest of this is still the same stuff. That is our rate constant, and that is our time. Now, also different is the half-life equation for a second order reaction, and it is this one right here. The half-life is equal to 1 over the rate constant times the initial concentration. So the half-life is dependent on the initial concentration of your substance there, your reactant. And again, that's different than first order, which is independent of the concentration. There's no concentration sort of value. Since it is 1 over the concentration, basically, right, that means that when my concentration increases, what happens to my half-life? It decreases, right? Yeah. And when my concentration is smaller, I will have a longer half-life, right? So, and that is sort of the relationship that we see here. And by the way, you can just figure that out, which is regular numbers, like 1 divided by 10 versus a 1 divided by 5, and you'll see the difference in that. Since this is a constant, doesn't really change for either of those two. So yeah, so obviously a larger initial concentration here in the second order will actually see, again, that half-life being faster than if we had an initial concentration. We also can take that integrated rate law and we could rearrange it in the form of a straight line, and that would be 1 over A is equal to KT plus 1 over A naught. And that would be the form of a straight line. That is our Y is equal to MX plus B. And that gives us really our linear sort of graph that we associate with a second order reaction. On the Y, you're going to graph 1 over the concentration of A, and on the X, it will be our time. And in this case, we actually get a line that has a positive slope. And that means in this case that the slope is actually equal to the rate constant. And that is why we'll get a positive rate constant again here in this case. So this one's a little bit different. The slope of that line is not equal to minus K. The slope of this line is just equal to K because it's a positive sloping line in this particular case. So much like the other one there for first order, you do need to know really those kind of 4 important things. Our units associated, right, with the rate constant, our rate law for the second order there, and our half-life, and obviously our graph, right, that is associated with that. And again, that is a different graph than what we saw with our first order, which was the natural log of A versus time, giving us a negative straight line sort of sloping graph. Any questions on that one there? The last sort of common orders of reactions that we come across is zero order reactions. And zero order reactions also has its own kind of set of equations and graphs that we use. And let's talk a little bit about this one here. So for a zero order reaction, we can get it, obviously, as we talked about. We could have a reactant where it has an order of 0. And as we mentioned, that obviously equals 1 in this case. So just like the other first order and second order, zero order reactions will have specific units for the rate constant. And because basically it equals 1, you basically get the rate is equal to the rate constant in this case. So when you see a rate constant has units of molarity over second, that is typical of a zero order reaction. Now, in this case, it also has an integrated rate law of concentration versus time. It looks just like the first order one, except there's no natural log happening here. So it's basically the same one, just no natural log. It also has here a half-life equation where the initial concentration divided by 2K. And in this case, just like second order, the half-life is affected by the initial concentration. But in this case, when we increase concentration, what happens to the half-life? It gets larger, right? Yeah, and this so it's kind of opposite of the effect that we see with it on the bottom there of the second order. And again, you could just figure that out by taking 10 divided by 2 or 5 divided by 2. You can see the difference for what the half-life would be. Now, once again, we could also rearrange this equation to fit a straight line, and it will look something like this: minus KT plus the natural log of A naught. And once again, that is going to be our y is equal to mx plus b. So that means on this graph here, we're going to graph the concentration versus time. And this will yield us a linear relationship where the slope is equal to minus k. And once again, here we're back to the slope equaling minus k because our line is a negatively sloping line. So those two negatives will turn our rate constant into positive. Yeah. Where did natural log go? It came from me writing the wrong thing. Thank you. Yeah, thank you. It should be that. Thank you very much. Yeah, so don't do what I just did there. And so zero order, no natural logs in there. So it should be concentration equals minus KT plus the initial concentration there. In this case, we do have that negatively sloping line. Now, this graph, if you remember, is also the same sort of graph that we saw for a first order, but it did not look the same. So if you remember, if you go back to our first order sort of graphs, you will see that graph of concentration versus time, but it does not give you a linear relationship, right? It gives you that one where we kind of see it decreasing with time. So you don't get that linear relationship. So it is possible you may see the same sort of graph for both first and zero in terms of what is being graphed, but only one of them should give you a linear relationship, and that would be zero order. It should give you a linear relationship when you graph concentration versus time. So if you graph concentration versus time, you really don't get a linear relationship. It's probably not going to be zero order. It might be first order, most likely. Yeah. That is, yeah. So if we go back and take a peek at that one there. Next slide here. Oops, there's. Yeah, so if we look at it, this is the same sort of graph that we just looked at with zero order, which is concentration versus time. And as you can see, it's not a linear relationship. So more times than not, when we talk about sort of graphing in first order, zero order, or second order, we usually want to look at that like the linear relationship. So more times than not, when people talk about the graph associated with a first order, it is the natural log versus time that should give you that linear relationship. But sometimes people will still do the other graph occasionally for first order. So again, if you did lay up a graph like this and you see, like we see here, that it is not linear, then it wouldn't be zero order. Most likely, probably might be first order that we're dealing with. Other questions or not? Okay, so much like all the other ones there, we do want to make sure we know the four kind of basic things here. Our difference in our rate constant units, obviously the specific one used there for zero order for concentration versus time, our half-life, and then obviously here the appropriate graph that should give us our linear relationship for zero order. And again, in terms of graphing, most of the time we do try to look for in kinetics, again, that linear sort of relationship. So that's why we sort of always kind of rearrange these things into that y equals mx plus b to give us that straight line and linear relationship when we graph things. All right, so let's take a look at one here. We got Q going to 2R, second order. If the initial concentration of Q is 0.01, after 5 times 10 to the 2 second order, which obviously they would need to tell you in this case, since we are looking for the rate constant, so we don't have the benefit of seeing the units of it. So we definitely want to use our equation here that does our concentration and our time. And again, remember that it is positive here, not minus, which is a common mistake. Here we do have our initial concentration and our final, and we also have our time, so we could plug it in. We're gonna take a 1 over our final, which in this case is 0.001 equals 1 over our initial 0.01 molar. Too many ones. All right, plus our K, which is what we're looking for, and our 5 times 10 to the 2 seconds are 500 seconds. So here I'm going to basically do 1 over this number, and then I'm going to take this to the other side and subtract it. And when I do that, 1 divided by 0.001 minus 1 divided by 0.01. That's going to give me 900 over here. Units would be 1 over molarity at that point is equal to K times our 500, basically. We're then going to obviously divide that to the other side. And when we divide that to the other side there, looks like we will end up with a rate constant of 1.8. Units here would be 1 over molar seconds, which is what we would expect, right, for a second order reaction. Any questions on that math there? Okay, so I'm gonna say you shouldn't. So again, if you're gonna punch this into your calculator, the way I would do it, I would take 1 and then divide it by 0.001 to do numbers. Yeah, okay, yeah. So again, I would, like I said, I would do it, this guy here and then hit equals and then hit the subtract button. I would also open up some parentheses if I was doing it on my calculator there and do parentheses 1 divided by that number and hit equals. And then obviously you could divide it by the 500 at the end. There are questions? All right, so these are, again, the most common sort of orders that we come across in terms of reactions. As we talked about, most reactions have, maybe 2 or 3, 1, 2 or 3 sort of reactants. So we typically don't commonly see in a lot of cases really giant overall orders of reactions. And these are very common ones. So this is a nice table, sort of summarizes the information that you need to know in terms of the equation and the half-life for both our 0, first, and second. Once again, in all these cases, you could substitute in A naught divided by 2 into here or there or there, and solve for T to get to our half-life equations if you wanted to. Also, graphically, as we talked about, you do need to know the 3 sort of graphs that are really associated, one with each of these. Once again, if we have 0 order, that is going to be our concentration versus time, giving us our negatively sloping line. If we have first order, that would be our natural log of A versus time, also giving us a negatively sloping line. And again, if it's second order, that would be our 1 over A, giving us a, not that way, giving us a positively sloping line going in the other direction in the positive way. Let's try that again. Let's go that way. There we go. Where the slope is equal to K, and this obviously would also be time. So graphically, we sometimes will use obviously a graph to determine maybe what the order of the reaction is. And you'll actually do that, not in the upcoming experiment, but the one following that. So if maybe you did a bunch of experiments, you can then basically do all three of these graphs for your experiments, taking one over to concentration versus time, or natural log versus time. You do like a best fit line using Excel or something like that, get the equation, the R squared value, which is the linear coefficient, and the one that is closest to 1. Right, when we do like a best fit line, like on Excel or something like that, we get the R squared value. That's the linear coefficient. Closest to 1 is perfectly linear. So the one that is closest to 1 in terms of its R squared value would be the one that's most linear. So you can sort of graphically determine what the order of your reaction might be. Any questions on that there? So what we're going to talk about now is sort of the relationship between sort of temperature and rate constants and the rate. So before we get into that, let's talk a little bit about some of the important aspects of reactions in terms of energy, and that is exothermic and endothermic reactions. And as we hopefully know, exothermic means we are releasing energy, right? And endothermic means we are absorbing energy. Okay. So these are what are sometimes referred to as energy diagrams, as you might be familiar with. We basically have our reactants and we have our products, right? So in a reaction, we go from reactants to products in this case. And as we see on the diagram here on the left, our reactants are higher in energy than our products, right? So the only way for us to get down in terms of our products is overall energy needs to be released in that case, right? So that is why it's an exothermic reaction. On the one on the right there, that's an endothermic reaction where we have our reactants and our products. And in this case, we see our reactants are actually lower in energy than our products, which means the only way for our reactants to get up there to our products is we need some energy to kind of flow in, which is why it is overall endothermic, right? Speaking of energy for reactions, right? We usually refer to that as delta H, which is the enthalpy, right? Or the change in enthalpy. And if it's an exothermic reaction, the delta H should be positive or negative. Should be negative, right? And if it's endothermic, the delta H is a positive number, right? Now, we actually get that by taking the energy difference, right, between where the reactants are and where the products are, right? So that difference right there is our delta H of the reaction. Same thing over here, difference between these two guys here, right? And as you might remember, when you calculate delta H of a reaction is basically the delta H of your products, right, minus the delta H of your reactants, kind of where you end up and where you start, right, in a reaction. So when we do anything that's sort of thermodynamically related, like delta H, it's all about state functions, which means it doesn't matter how you get there, it just matters where you start and where you end, right? And in a reaction, again, our products is where we end and our reactants is where we start. So that's why we do products minus reactants in a lot of those type of calculations. And that means that when we look at it in terms of energy, our products are lower in energy than our reactants, which means that should give us a negative number, right, when we subtract that. So that's why our delta H is negative. And that's opposite of what we see in the endothermic. Our products are actually higher in energy than our reactants. And that means when we take the difference of those numbers, we actually should get a positive number. So in case you ever wonder why that is, that's why you have a negative on one and a positive on the other in that particular case. Now, when we do have a reaction that takes place, there's really a couple things that need to happen for an actual reaction to take place. There does need to be a collision, right? So they actually have to kind of come in contact with each other. Collision theory is sometimes referred to. They actually do have to hit each other in the right sort of location, like the active side of each, for a reaction to actually occur. The other thing that actually has to happen is they actually have to hit each other with the right amount of energy. So there's a minimum amount of energy that's required really for that reaction to take place. And that's what is sometimes referred to as the activation energy. So sometimes people think all you need is for those things to sort of collide with each other. And that's not always the case. And just because things sort of collide with each other, it actually doesn't mean that you will make products in that case. But you have to have basically both of those things occur. You got to kind of hit each other in the right location, and they got to hit each other with the right amount of energy for a reaction to really take place. So again, not all collisions will result in products being formed just by throwing those things together. So when we have a chemical reaction, the only thing that happens as we go from reactants to product is what happens? How do the reactants become the products? What happens? Yeah, bonds are first broken and then they're formed, right? So in a chemical reaction, right, the only thing that changes is basically everybody's location, if you will. And to do that, the only thing that's changed is really the bonds, which is all about electrons. That's also why we have conservation of elements in our chemical reaction, right? Because the only way an element would change is you have to change the number of protons, right? So because chemical reactions all involve bonding and electrons, we never change those elements because it's all about the electrons and stuff like that. When we get to the nuclear chemistry chapter, it's all about changing the elements because all those are involved is protons and neutrons being involved in those type of reactions. But chemical reactions, it's all about electrons. So that means that the activation energy is actually the hill that the reactants has to climb to get to the other side. And that is what we see right here. That is the activation energy here, is that hill that our reactants has to sort of climb. And as they're climbing this hill, they're starting to break some bonds. And they're also starting to make some bonds. So as our sort of reactants sort of climb up that hill, they're starting to really break the bonds, and they're starting to make some bonds till they get to the very top of the hill here. And that is what is sometimes referred to as a transition state. And it will make this little guy up on the top here, which has like that little weird symbol next to it, something like that. Yeah. And this is what is sometimes referred to as a transition state complex or an activated complex. And a transition state complex is a substance that basically has, at this point in the process, partially made bonds and partially broken bonds. So it's sort of in a transition state, hence the name. It's in a transition state of kind of converting into products before it comes back down the hill. That is also the highest part in terms of energy, right? That sort of top of the hill. And in chemistry, right, things that are high in energy, is that typically stable or unstable situation? Yeah, things don't really want to be in the highest form of energy, right? So that's usually a very sort of unstable sort of situation. And that's why a lot of times those transition state complexes or activated complex are a lot of times very hard to isolate if you're trying to isolate, what you get kind of in the middle, because they very quickly want to get themselves down to a much better state of energy, and products are usually formed relatively quickly. So a lot of times it's very hard to sort of isolate those guys. And we see a similar sort of thing here on the endothermic. We are kind of progressing up the hill here. Once again, our activation energy difference between those two. And again, we have the same idea. We're starting to break and make bonds here on our journey up the hill. And we have our transition state complex on the other side, and we kind of come down the hill to the other side there relatively quickly. Now, the hill, right, that the reactants has to climb to the other side should have an effect on really the rate of the reaction, right? So we have something that has a really large activation energy and a pretty big hill. It's probably going to take a much longer time to get to the other side, because you will have a less proportion of molecules that have really enough energy to get up and over to get to the other side. So that reaction probably would occur a lot slower than, say, one where you have a much smaller hill or activation energy. That would mean that there's probably a greater amount of reactants that have enough energy to get to the other side, and that would result probably in a increase in rate. That's also why when we increase the temperature, we typically will see the rate increase, because when we increase the temperature, we have now increased the amount of reactants that have enough energy to get to the other side. And we get a greater amount of guys going to the other side, and we see a much increase in the rate of the reaction. And vice versa, if we kind of throw everything on ice, we're going to really see sort of the opposite effect, right? You now will have a much lower, probably, proportion of molecules that have enough energy to climb up and over the hill to get to the other side. And we'll see really a decrease in the rate of the reaction. We also see here, just in the comparison of exothermic to endothermic, the one that has the greater hill is which reaction has the greater activation energy? Yeah, endothermic, right? And that also sort of makes sense because it's endothermic, which means kind of need energy put in overall, right, to kind of help it along a little bit. So overall net, right, we kind of need some energy to put in. For our exothermic, we sort of have enough energy a lot of times, and we have a little extra energy left over at the end of the reaction. The other important thing is when we look at this, where activation energy is, should activation energy be a positive number, negative number? Does it matter? It is a positive number. So in each case, right, from our reactants to the top of the hill, you're putting energy in, right? So activation energy should always be a positive number, yeah, as a result of that. So keep that in mind as you're doing calculations. When you calculate it, you pretty much should hit a positive number for activation energy. Any questions on any of that there? So there is a relationship between temperature and the rate of reaction. This is what's sometimes referred to as the Arrhenius relationship or equation. And this is one version of it. We usually don't use it too much, this version of it. We'll take a look at a version that we use a little bit more in just a second. But there are a couple of things here that we will see in all versions of this equation. First off, we do have the capital T there, which is our temperature in Kelvin. So much like anything else in chemistry, got to make sure that you get it to Kelvin. This is our gas constant, and once again, it is the gas constant that is not the one you use for the ideal gas law. This is the one that involves energy, so that is the 8.314 joules per Kelvin per mole. So you want to make sure you use that one and not the other one. A is the frequency factor, and you can kind of think of the frequency factor as really what we've sort of been talking about, really the kind of the proportion of molecules that have enough energy to kind of get up and over to the other side. E of A is our activation energy, which is, again, what we were just talking about, that minimum amount of energy that's required. Now, when we want to speed up a reaction, as we were talking about there, and just take a look back here. Another thing that could kind of affect this, since I have this diagram here, we'll take a look at it, is the rate of reaction is we can add a catalyst, as we talked a little bit about at the beginning of this chapter. A catalyst, again, is not a reactant and it's not a product, and it does not get used up in a chemical reaction. But what a catalyst is able to do, as we might have mentioned a little bit earlier, is it's able to find sort of an alternative pathway for that reaction to take place. So be it allows everybody to kind of come together in a more efficient manner and stuff like that. But what it actually will do in terms of sort of our energy diagram and all that is a catalyst will actually be able to lower the activation energy. So when we have a catalyst involved, by finding that sort of more efficient or alternative pathway for that reaction to occur, what it's able to do is basically kind of lower the overall activation energy. And that, by in turn, will do is allow greater amount of reactants, right, to have enough energy now to get to the other side because it's a much smaller hill. So the use of a catalyst will do that for a chemical reaction by finding that alternative pathway and lowering that activation energy hill. So when we look at this, as we've been talking about, there's that energy barrier, which is that activation energy. And at the very top of it is where we find that really that intermediate that has that partially made bonds, partially broken bonds that are happening. And for example, if we were to look at sort of this guy who's really just sort of rearranging itself, we're kind of rearranging the carbon and the nitrogen in this isomerization here of this molecule. What will happen is as it's progressing, it will start to break the bond between the carbon and the nitrogen here, and that will allow this guy to really start to sort of rotate as it goes through it. So as it's coming here, it starts to break this bond. It's starting to rotate, having partially made bonds as it's rotating around. And again, it will come back down the hill. So here we see our activation energy for this particular rearrangement. We see overall our reactants are higher in energy than our products, which means this delta H value should be positive or negative. Should be negative, right? And it's going to be an exothermic reaction, right? Again, reactants higher in energy than products in this particular case. All right. So let's take a look at that equation, Arrhenius equation, and maybe another way that we commonly will use it, which is this. And this is the graph that we see, the relationship between the rate constant and the temperature. So what we see is at a lower temperature, we have a much smaller rate constant, right? So again, the reaction will probably occur not as fast. There will be a less, I'm sorry, that we see a smaller rate constant at that lower temperature. At the higher temperature here, we see a larger rate constant. So at the higher temperature, we see a larger rate constant. So we have a greater proportion of molecules that can get to their side. Again, at the lower temperature there, we see a smaller rate constant, which means we have less, guys that can kind of get to their side under normal conditions. So we do see that sort of increase in the amount of reactants can make it to their side. So we could come through the Arrhenius equation here and sort of natural log it up. And we get this equation, which is one version of the Arrhenius equation. And I will say this is the version of the Arrhenius equation that we use for graphing for the most part. And it actually is in our favorite form, which is our straight line form, our y equals mx plus b. And when we make this sort of plot, y is equal to mx plus b. On the y, we would graph the natural log of k. On the x, we would graph 1 over the temperature in Kelvin. And this will actually yield us a straight line. And it would actually be a negatively sloping straight line, where the slope, as you can see there, is equal to minus E of A over R. Once again, I have a negatively sloping line, and that equals negative E of A over R, which means my activation energy should be negative and negative, which will give me a positive number when you take it off the graph. So again, when you do this, it'll give you a positive number. Now, there is definitely, when we use this equation in whichever form that you use it in, we do have to watch units. And let's talk a little bit about this part of that formula, which is this. Typically speaking, the activation energy is oftentimes given to you in units of kilojoules. And our gas constant is in units of joules, joules per Kelvin per mole, but basically joules. You are 1,000 factor off on each of those. So when you're doing any type of math that's using both of those together, you do need to do a conversion in most cases. So I personally convert everything to joules when I'm doing the calculation, then take it back to kilojoules at the end. But you can convert R into kilojoules as well. So whichever way you want to do it, but you do usually need to do some type of conversion, otherwise you'll be off. That also means that basically when you do solve for the activation energy using a graph, the activation energy will equal minus the slope times R. And the units I would get out of this, if I did that calculation, are going to be in joules, because R is in joules. So if you take your slope of your line and you times it by 8.314, the units that you will get are going to be joules per mole, but joules basically. So you want to keep that in mind as well. So sometimes people kind of mess up on that joules, kilojoules sort of conversion. So you do want to watch out for that. Any questions on that there? So here is a actual Arrhenius plot here. And again, we can see on the Y there, we have a natural log of K and our 1 over T in temperature in Kelvin. By the way, again, this is Y is equal to mx plus b, which means if I wanted to solve for A, which is the frequency factor, right? The natural log of A would equal the B, which is the y-intercept, right? So that is where that line crosses the y-axis. So you could also, from a graph, figure out the frequency factor, which again is that proportion of molecules that have enough energy to get up to the other side. You basically would be doing a little of that E action that we did in one of those earlier problems to kind of solve for the activation energy or the frequency factor. By the way, the frequency factor in terms of units typically will have the same units as K has. So in that particular problem, whatever K has for units, 1 over seconds, 1 over molar seconds, whatever it may be. Typically speaking, if you're sort of graphically solving for the frequency factor, it will end up with the same units as what you have there for K. And that's because it is the y-intercept, right? Which means it crosses the y line, which means the only units of natural log of K are none. There's no units of it. But when you take the E of it to get back to a number, it goes back to basically K. And whatever the units of K were would be what your units of your A would be in that case. So when you actually mathematically solve for that A, you're actually restoring the sort of units that were associated with the rate constant. Any questions on that there? Okay. All right, so that's a lot of stuff that we just talked about there. So again, adding that extra energy obviously allows the greater proportion of molecules to get to the other side. So typically speaking, if you increase the temperature of a lot of reactions, not all reactions, by like 10 degrees Celsius, you can see a doubling of it. And again, the opposite is true. If you decide to throw all your test tubes on ice, you're going to slow down it, right? It'll be like removing energy from it. And that's what we see here. This is a graph of 2 different temperatures for the same reaction. And I sort of scribbled on it previously, but in the first temperature, which is the blue line, which comes to here, we only have about that fraction of molecules that have a sufficient amount of energy to get up and over to the other side. By increasing the temperature, what we can see is, in addition to those guys, we now have that amount of reactants that have enough energy to get to their side. So again, increasing the temperature increases the energy, gives those guys a much greater amount of energy to get to their side. Here's the same equation in case you missed it the first 3 times. So let's take a look at it, an example of, how we would solve it using a graphical approach. And by the way, in this chapter, you may have to open up some Excel and do some graphing to solve some homework problems and stuff like that as you go through it, since they like graphs a lot in kinetics. So don't be surprised. The only way they sort of solve some homework problems is you might have to make some graphs or something like that to help you out to do it. So let's say we have this table, and this table is actually quite nice in the sense that they were nice enough to give our temperature in Kelvin, but a lot of times you will find tables in Celsius. So a reminder, you do need to add your 273, right, to get yourself to Kelvin. So if you happen to have a table where you have all the temperatures in Celsius, you got to first convert it to Kelvin. Then you need to take all those values, right, and take 1 over the temperature in Kelvin, right? So you would then obviously need to transform all the values that you see in this table and take 1 over the temperature. Now for our K here, you would need to take all those values and basically take the natural log of each of those values. When you do that, you would go to your graphing program there, do a graph where you'll have like a best fit sort of line. And that would get you your natural log of K over 1 over T. And you'll get your y is equal to mx plus b. So if you did that, you will get a graph that looks something like this here. And obviously that is the equation that comes from the best fit line that we see. Again, we can see this graph typically gives us a negatively sloping line when you graph the Arrhenius plot. in this particular case. So if we were going to use this to determine the activation energy and the frequency factor, we can use our equation here to do so. We know that the slope of this line should equal minus E of A over R. So we can obviously take the slope, which is this number right here, right? And we could use that to solve for what we're looking for. So the slope in this case would be minus E of A over R. Our slope in this case is minus 1.12 times 10 to the 4 equals minus E of A, which is what we're looking for, and our gas constant, which is this guy here. We'll multiply it to the other side there. And we'll take basically 8.314. Punch it in correctly would help. 8.314 times 1.12 to the 4th. We also have not only 8.314 going to the other side, again, the negative has to go to the other side as well. That's going to give us our activation energy here as 93116.8. Reminder that this is really joules per mole, really. Kelvin kind of goes away somewhere in there as well, and when you do the division. So typically speaking, like I said, kilojoules is typically what is given in. So you could divide that by 1,000 and get yourself to 93.1 joules as our activation energy. And again, here we have a positive number here for the activation energy. It would be. See, I'm just leaving things off today or putting extra things in. Thank you. Kilojoules per mole. You know, I never really took chemistry. It's okay. Don't worry about it. They're like, you know how to use a key? Yes. Can you find the building? Yes. So you're hired. All right. So that works. I was more of a history major. What can I say? It's all right. All right. So let's also do the frequency factor. So our frequency factor, again, would be here. And again, that's going to give us that the natural log of our frequency factor is equal to our y-intercept. So in this case, 26.8 is what we're looking at. So we want the natural log of A is going to equal 26.8. Again, we're going to take the E of both sides, and that will give us our frequency factor here of something here. Yeah, we'll go with 4.36 times 10 to the, looks like 11. Now, again, as I mentioned, in terms of units, really natural log K won't have any units. But when we do the E part of it on both sides there, we kind of put the units back in. And those units would be the same units that we see here for the rate constant. So those would actually be the units that we would use here for our frequency factor as well. Any questions on that there? So this is the Arrhenius equation where you would typically use this formula in sort of a graphing situation like we just saw here. Obviously on an exam or quiz, I would probably not give you graph paper and have you graph it by hand. Unless I'm really mad at you, but I probably want to do that. But maybe you might be given a graph and the equation, so you need to know obviously from that how to do that. Get the information from it. Now in a homework problem, you might need to make the graph yourself and stuff like that. Okay. Any questions on that? Now, yeah. What's that? Yeah, so usually that's the button like we used earlier. It's usually on most people's calculators like above the natural log button. So that would be what you would put in there. How would you put that in? I would hit on most people's calculators, you probably got to do like the second or shift button and log, and it should pop up like an E and a caret. And then you just go 26.8 and hit equals. Other questions? Okay, so in a non-graphical sort of situation, we don't always want to make a graph, but maybe we have some information about 2 points that may be along this particular line. So there is a non-graphing version, or sometimes referred to as a 2-point version of the Arrhenius equation, and that is the natural log of K2 over K1 is equal to our E of A over R, 1 over T1 minus 1 over T2. Once again, in unit wise, we do need to definitely be careful on this one, since it's going to probably be a straight calculation. I just going to write the right things down there, maybe. That's kilojoules and joules in that case. These temperatures obviously need to be in Kelvin. And it is, you divide the numbers first and then take the natural log. So don't take the natural log of each of them, then divide it. So divide the number on the rate constant. Now, clearly the K2 and the T2 temperatures should be the ones that go together. Yes, so you got to kind of keep those together. So if you have two values, two K values, two temperature values, it really doesn't matter which one you call number one and number two. You just got to keep the appropriate numbers together that go together. So whatever K value goes to that temperature, you could call it K1 and T1, or you could call it K2 and T2. They'll all come out the same in the math works of it, but you can't mix and match. So when we use this equation, we do want to be careful of that E of A over R. And I think we will lay it up there.